Hi, my name is Guy Fedorkow. I want to talk today about some work we've been doing at the jointly between MIT and the Computer History Museum. There was a machine built in 1950 called Whirlwind, and we have been recovering some of the context and software from that machine. And I'll talk a little bit about that, and in particular, a specific application. There was a demo done in December 1951, which was, I think we would all say, turned out to be significant. So with that, I'm going to start with a bit of history. A lot of the Whirlwind work centered on air defense, and air defense itself has kind of a history. Airplanes, of course, started appearing in World War I, but by World War II, aircraft were strategic weapons, very important weapons. It was immediately discovered that it's kind of hard to protect against an aerial attack because, you know, they don't have to worry about what the ground is like and so on. They just fly over you and drop stuff. So there was a strong thread in the military that the best way to defend against aerial attack was to destroy the other guy's airfields before they could take off, right? Okay, that's a theory. But with the Battle of Britain in the UK, it had to be admitted that actually air defense on the site had helped quite a bit to blunt the attack. So it was, you know, there was some of each that had to be pursued. During World War II, of course, and immediately thereafter, air defense was a European problem because it was a long way to get here and to the US, and that was over there, and, you know, it's their problem. 1949, the Soviet Union exploded a nuclear bomb. And around that same time, they also started designing actual airplanes that could, you know, perform pretty well. And suddenly in the US, it was, uh-oh, that could happen here. Oh my God, what are we going to do? So the US Air Force, which had just recently been formed at all, quickly got the message that they better actually think harder about this air defense thing. And consequently, they started a number of programs to figure out how do we defend the North American continent from Soviet bombers carrying nuclear weapons. So the initial task or the initial mandate for the Air Force was choice one in air defense, that is the Strategic Air Command, which means we will go blow up their air bases before they can get to us, which is fine. But once the nuclear threat became tangible, it was, I guess we got to take this defense thing seriously. So a variety of committees and study groups and so on were formed, projects were spun, research was done. The ones that matter in this context, there was a thing called the Air Defense System Engineering Committee, which was founded, run out of MIT with the Air Force, led by a guy named Dr. George Valley. They pretty promptly produced reports on the state of air defense, which was not very good, and started working on proposals for what would be a better way to defend, what would be a good way to defend the US airspace. There were two prominent development labs, one at MIT and one at University of Michigan, Michigan Aerospace Research Mark. Anyways, in a lab called Willow Run. Initially, the Air Force thought they were going to pursue both of these projects, and ultimately, the work became, of course, so freaking expensive that one or the other was going to survive and the other was not. The Willow Run proposal started with a British system called the Comprehensive Display System, CDS, which was designed to coordinate defense of a naval battle group, right? So a more or less point, small area to be able to watch everything coming at it and coordinate among the various attackers, assign interceptors to attackers and keep track of them. Willow Run decided to start with that and extend it. It was completely analog technology at the time that they picked it up from the British, and well integrated with radar, but definitely a manual thing, right? That it was an assistance to keeping track of what was going on in an air battle, but it didn't try to do anything about it. It just kept track of it all for you, helped to keep track of it when there was more than a couple of fighters in the air. Willow Run, of course, discovered that this is not easy to scale to a continental problem with aircraft that were starting to get to be supersonic speeds, but that was their plan, so that's what they worked on. MIT had a little bit different course. There was a machine developed at MIT called Whirlwind that had initially been developed under a Navy contract for a completely different purpose. But the Air Force came along and got convinced by Dr. Valley and others that Whirlwind would be a good starting point for a computer-based air defense system. This is, to me, a miracle of salesmanship. The machine barely worked, and in 1950, there were not many computers around. Right? So somehow, they convinced the Air Force that they should not pursue this plan, which was based on technology that they knew worked, and that they should instead invest in Whirlwind, in the MIT development. MIT, of course, did get the contract and worked like heck on it. That evolved through several organizations until it turned into what became the SAGE air defense system, which, of course, was a very expensive project and well outside the scope of just what MIT could do. So that caused the formation first of Lincoln Labs and then of MITRE Corporation and then SAIC. So by 1953, there was a showdown. Willow Run continued substantial work on the Beaumark missile system, which I'm sure much to their chagrin ended up being controlled by SAGE, among other things. But Lincoln Labs and MITRE won the contract and of course pushed SAGE through to deployment. What I wanted to do with this talk is go through the demo, which would have been the critical element in convincing the Air Force that this piece of technology that barely worked could actually had the promise of doing what they wanted it to do and scale to a national system. Okay, I should have said this talk is in 3 parts. That was the history part. This is a brief introduction to the machine itself. I'll try and get through this part relatively quickly so that we can then talk about the air defense demo. And I'm glad to come back to any of the material on this, about the machine as well as if there's time for questions at the end. Okay. So Whirlwind, it was a one-of-a-kind machine built as a research project at MIT, starting in about 1947, and first operational in about 1949, towards the end of the year. It became reliable enough to be seriously running by 1951 and stayed in service till 59 at MIT. The project began under contract for the Navy. As I said, the initial application was a real-time digital flight simulator. Right? This was in the day, of course, when flight simulators were levers and gears and wheels and belts and analog stuff. And a couple of visionaries in the Navy saw, maybe if we could use one of these computer things to simulate the aircraft, then we wouldn't have to build a new simulator every time there was a change to the aircraft. The interest from the start was in using this machine in real-time applications, and that also was quite unique. As the few computing machines around in 1950 were used for numerical analysis kinds of problems, like the Manhattan Project kinds of things. This was quite a different idea, where we were going to actually plug a computer into inputs and outputs and have stuff happen. This came out of a thing at MIT called the Servo Mechanisms Lab, and that might give you a hint as to why this came about. The machine itself is a 16-bit parallel architecture. This was at a time when everyone else was doing serial machines, with an architectural address space of 2,000 words. They could do about 50,000 ads per second, which was way faster than anyone else. So this would have been, for a time, the fastest computer on the planet. Although it's not part of this story, Whirlwind is credited with the development of magnetic core memory as well. That's why most people know the machine now, is because of the introduction of core memory. It was a research program, right? There was no pretense that they were building a prototype to go into production. These were research applied mathematician guys. And the machine was used for a lot of different things on campus. The Air Force got the good hours in the daytime, and researchers of all sorts got the 3 a.m. shift. Just a brief history timeline. They started the aircraft simulator idea in 1944. They got far enough, the machine was going well enough to start demonstrating equation plotting on a CRT in 1949. In 1951, they did this radar-guided air intercept demo. 1953, they had quite a credible demo that was used to vanquish Willow Run and get them out of the race. Also in 1953, they started installing core memory on the machine, and at that point it became much more reliable. And 1959 it was decommissioned. If you were going to do a science fiction movie about a computer, then this would be the control room you would want. The machine, let me see, the machine itself, I think I've got a floor plan. Yeah, that's right. Okay, the machine architecture is spookily familiar. Right? This is, if you look at ENIAC, a lot of people in this room would look at ENIAC and say, I guess it's a computer. But this block diagram, you'd say, well, that's obvious. It's a computer. It's a program counter. It's got memory. It's got an ALU. It's got I/O devices. One might note that Ken Olsen and Harlan Anderson worked on Whirlwind and left. Where did they go? DEC. And MIT teamed up, let's say, with IBM to do SAGE. So the two dominant themes of computer architecture prior to the microprocessor world both had roots in this machine. It was physically kind of large, right? Vacuum tubes, 2,500 square feet, about 100 kilowatts of power. And this was just the part on the second floor. The basement was full of power supplies. Whirlwind had a lot of I/O stuff attached to it because of their real-time focus. They kept on bolting more stuff onto it. A lot of it is the normal thing that you'd expect. A couple that are relevant here is they were right at the start of what we would now see as interactive graphics on computers. So they used large oscilloscope tubes for graphical display, and they invented what they called a light gun, which when you see it, you'll say, oh, okay, that's a gun, but evolved into a pen and on from there. Yes, the gun. Right, so on the left is the large oscilloscope displays they used. These guys knew everything about radar, so this would be derived from radar technology, of course. And then on the right is a prototype of the so-called light gun. Point and click. Point at the screen, click the button. I'm intrigued. By the time I got to SAGE, it's obvious that IBM had an industrial designer on hand. So the IBM light gun, actually looks like somebody actually worked it through, did a design. The graphics system was wired in from the start. The first demos, when they first got the thing to work, the way they knew it was working was because they could plot equations on the graphics display. It did not print Hello World. It did have a console attached to it. We were discussing earlier, they didn't even connect the keyboard until 1956. All right, so the focus was buttons, lights, CRT, and I don't want to overemphasize it, but the light gun was an important part of it. Right? It is not a point-and-click computer, but they did use the light gun for interactive input. The graphical system is astonishingly simple. You take two D2A converters, you connect them as I/O devices, and if you want to point on the screen, you put the X and Y into the two D2A converters and you turn on the intensity for 50 microseconds. And if you want a point to stay there, you keep doing it. And if you want the point to go away, you stop doing it and it'll go away. So it was entirely up to the programmer, of course, to draw the image and keep the image refreshed in a tight enough loop in the program. But it meant that the hardware was very straightforward. They ultimately ended up with an additional bit of hardware to draw short vectors, so points and vectors. I think everyone in this room knows the kind of timeline of how this kind of stuff has evolved. I won't go over this, but I think of Whirlwind as the slowest Arduino you've ever seen. Right? It's the 2K space, 50K of non-volatile storage, 16-bit architecture, et cetera, and so forth. But compared to the math tables project with 450 people in a room with calculators, this is really fast. Right? It's just astonishing. Okay. And you don't have to feed it each one a sandwich every day. Right? You just give it electricity. Okay, so what are we doing here? We have the MIT Archive and Museum has about 2,000 documents archived from the Whirlwind program. There's a lot of written material. It's not complete, but there's still quite a bit. The Computer History Museum has hundreds of tapes, paper tapes and magnetic tapes. The physical machine was mostly destroyed around 1970, so there are bits and pieces around. There are quite a few pieces in the CHM collection, and then you'll find little bits and pieces of Whirlwind all over the place in offices and people's small displays in various prominent places. So the machine is gone. There was an interesting story about how that happened, but we'll work on that some other day. So obviously what we want to do is see how do we combine all of these things and learn something useful from it. How did we program this machine? Pencil and paper. So this was in an era where people originally first discovered that, programming, this is actually kind of hard. It was supposed to be that building the hardware was the hard part, and then you just write some code instructions, that's all. What do you know? That turned out to be a little bit harder than anyone thought. So at the start, coding was totally manual, right? Pencil and paper. Hand it to the typist. Typist types the paper tape twice, once to check. Programmer schedules machine time and loads the program. It doesn't work, and they bang their head against the wall, and maybe they have time to patch the tape, and maybe they don't, and they get scheduled for the next slot. There was a second thread of Whirlwind development, which was independent of the Air Force work, that was actively developing ideas of programming languages, right? It turns out they did not have the right one, it turned out, but they certainly were participants in that game, where at the time Fortran and COBOL both were being conceptualized, let's say. So, quote, automatic programming was the theme of the day, as it still is, of course. We're still hoping for automatic programming. Paper tape, thousands of them. Thanks to Al Casso here and Len Shustik, we have read essentially all of the paper tapes and 2/3 of the magnetic tapes, and it's too bad about that pandemic getting in the way when we were almost done with the magnetic tapes. But there's so far about 12,000 binary objects recovered, and matching up those objects with the 2,000 documents is, let's say, an ongoing project. This is the end of this section, but I just want to give you a sense for what the display technology could do at the time. One of the demo programs, which, no surprise, has zero documentation and no obvious provenance, was a game of blackjack that you could play interactively with the computer, actually using point and click, using the light gun. So this is the kind of display they could produce. There was a 7-segment character generator by the time they were done. And then each of those dots represents a hotspot that you can hit with the gun. So you can use this to play a game of blackjack. Our colleague here, Ken Sharif, actually took my simulator, converted enough of it into JavaScript. So if you log into that web page, you can play Whirlwind blackjack. and it's, it's a little buggy, but it kind of works. In the simulator, Ken's work is fine, of course, but the underlying code is not especially production quality code. Okay, part 3. Let me check my watch. Good, we're doing fine. So the Air Force is actually an interesting part of the story. That by 1950, the Navy was saying, didn't we fund you to make an aircraft simulator? What's this computer thing doing here? And MIT was going, yeah, don't worry, it's going to be good. You'll like it a lot. It'll be really cool. And by the way, they said, and here's the $3 million bill for this year's development work. And the Navy was going, excuse me, I don't think this is working quite the way we thought. Fortunately, the Air Force came along, and because of the political situation at the beginning of the talk, we said the Air Force was quite motivated. And while they didn't like the price, it turned out to be a bargain as a prototype for SAGE. So Whirlwind is, the total Whirlwind program came to, I think about $5 million. SAGE, by the time they were done, was in the range of $30 billion. So good price, great idea. Okay, so this part we've talked about. We've talked about the history part and MIT's argument that really this needed a network of computers to solve this continental-wide air defense problem of bombers coming over the pole. Okay, so there was a memo published in December 1951, authored by a guy named David Israel. And if you go to the registration desk, you can buy a badge that is like this Whirlwind one that has David Israel's name on it, and I think he's my hero. So David Israel was a guy who started pretty early in the Whirlwind program and stayed with the problem of using computers connected to radar to follow airplanes around. He did that through his entire career. Right? This work, some work before this on air traffic control, and all the way through the SAGE program. So this one guy follows the entire thing through as kind of a thought leader for what it should all do. This one document is a description of the particular demo program that they had in operation in 1951. And it includes the actual code, which I will say, I'll try not to say more than 27 times, fit into 256 words of memory. And those are 16-bit words, so not those cheap little byte things. And you can find the program, the document. It's on, in BitSavers. Thank you, Al. Okay, what are they trying to do? The problem statement is simple enough. Watch the radar for stuff flying around. Keep an eye. The operator's job is to identify all of the spots on the screen and decide which ones are attackers and which ones are potential defenders. The operator can then identify spots on the screen as either I don't care or that one is an attacker and that one is a defender. Right? In this version of the program with such a small amount of memory, they were able to watch, they could display as many points as there were coming back from the radar, but they could only track 2 of them. They could track the one attacker, and they could direct one interceptor to go after that one attacker. So the radar operator, of course, radar operator's job is to know which one is which, but the radar operator then tells Whirlwind, this guy, I want you to go get him, and that guy is the one who should do the going and getting. Right? So Whirlwind then knows which one they're trying to, which one is the intruder and which one he's going to use to go after it. These were all manned aircraft, but what happened is, the way they used this, Whirlwind would compute a heading for the interceptor. Of course, you can't tell the attacker what to do because they are not cooperative. But he can tell the interceptor what heading to fly to get to the attacker as quickly as possible, no matter what the course the attacker chooses. So the attacker can try and evade, but every second it recomputes the heading. In this demo, that computed heading was displayed on a light panel because everything was buttons and lights. It was displayed on lights, and the computer operator would get on the radio and talk to the interceptor pilot and say, hey, 302. And the pilot would fly heading 302. Okay, so that's what they're trying to do. We have this code working in simulation, and it's always useful just to review a little bit about what that actually means, because there's a lot of stuff there to make this work, including, of course, in the middle at the bottom, there is the actual Whirlwind instruction simulator, which is the easy part. But surrounding that is simulated airplanes, a simulated radar station. The buttons and lights, that's not so hard. And then the display system is, of course, simulated on a laptop. We actually have a demo of this that runs on a Raspberry Pi that works with a real oscilloscope, and it's kind of cool because you can, one of my colleagues in Germany made a light gun which we can attach to the Pi and point points on the oscilloscope. So that part might, that part could be is sort of real if you have enough gear at hand. Okay, so the display that the radar operator sees looks sort of like this. Whirlwind does 2 things during the normal operation. One is to simply reflect all of the radar returns that seem to be real points onto the screen, right? So that you see all of the aircraft. Radar, of course, is inherently noisy, so they spend a lot of time trying to figure out which points to bother with, which ones are static clutter and which ones are might actually be moving aircraft. But it displays all of the points that the radar system thinks are probably real. The radar operator then can use switches in the light gun to indicate which point to assign which task. And from there, of course, the text at the top there is mine, but on the light panel it will display the computed heading. Whirlwind also was equipped with multiple oscilloscopes, so you could draw similar pictures on multiple screens. So in this case, they used one screen to show everything in the air, and the other screen to show just the two that they were actively tracking. So when you hit the first, when you indicated the first one, it would appear on the second screen. When you indicated the second one, it would appear on the second screen. In this case, that's the two yellow dots. Oddly, I found after some very frustrating debugging that with no clutter, the program doesn't work at all. So, okay, we've added in a little bit of clutter. The problem is they're looking for aircraft in a, they keep track of approximately where the thing ought to be in a sector. And if it doesn't turn up, they don't know where the end of the sector is, and didn't close it out properly, so they don't detect it correctly. But a little bit of clutter is all it takes, and then it works, sort of. Okay. Right, so it does work. This is a modern spreadsheet analysis, of course, of what happens. The dark red line, is the track of the intruder. In this case, I'm not actually modulating the position of the intruder. The simulator now, we can actually steer the intruder. An operator, a competing operator can steer the intruder, but the default is it just stays on its heading. The yellowish line is the path that an interceptor should take if it was designated at that particular point in time to get the optimum intercept. The blue line is what it actually computes. So you can see here the way I set up this experiment, the blue line was heading due west because he didn't know what he was just going home for a cup of coffee. And at one point, at that one juncture, the radar operator diverted the intruder to say, "Hey, dude, turn around. Your job is to go after this guy with a heading 259." So we see that he immediately turns. I know only part of the reason now why that turn is not perfect. You'll see, of course, he turns too much at first, and then ultimately corrects and turns the right amount to, turn some more to come in at the right point for an intercept. The program measures the velocity of the aircraft, of course, because otherwise, how would you know when they're going to intercept? So it estimates the velocity, and since it didn't know which aircraft it was going to look at it didn't know in advance which one it was going to use as the interceptor because we didn't know, the operator didn't know. When it initially starts tracking it, it has to assume that its velocity is 0. And if the velocity is 0, then you have a very steep track to intercept with that orange line. So he starts out too far north, and then because it is a feedback system, because it came from the servo mechanisms lab, every cycle they do it all over again, and they get a better estimate of the velocities and the angles, and they close the gap. Right? So it does work. I think there's something that's a little bit more than that making this not quite right. I think maybe some of the geometric approximations are a little rough. I mean, this does fit in a very small amount of code, and you have to do sine, cosine, arctan, and none of those are easy. But anyways, that's where this one is at. As we said, it's working. It's not completing it. It's not computing the track quite right yet. Occasionally, this is ironic. Occasionally, I don't know how to reproduce it. Occasionally, when I run the thing, manually with manual input to set the flight paths and so on. Occasionally, the interceptor. This is amusing. The interceptor flies exactly the wrong direction. And of course, I'm going, well, okay. So he looked at what he was coming at, and he said, that's good, I'm out of here, I'm done. But no, there's probably a sign problem in there somewhere where it's doing the arithmetic upside down. This program is hard to debug, even now, right? I can throw billions of cycles at this, and it is hard to debug. I don't know how they did it, right? It runs in real time. They did have analog recorders. They used multi-track analog recorder to record the radar scenario as the simulation, as the real thing played out. But you still can't single step it. I mean, they can do it over again, but they didn't have scripting languages, so they could only do it over again as well as they could remember how to, when they clicked what. If you put in a breakpoint, it stops and you're done because the radar moves on. This, to me, represents a tour de force in debugging. Say it's only 256 words, okay, but it is, to my mind, quite complicated code. And I don't know how they did that part. And I think that is the end of this talk. There was a ceremony at the end of the machine's life at MIT to decommission it, and they did not pull the pin. The actual event, I think, happened in late May 1959, so no one had to be there to find out whether the pin was really going to get pulled on June 1st. And with that, I'll ask if there are questions. Yeah, so we're going to ask that Jeffrey bring the microphone to whoever is asking so that it gets on.
Okay. I'll come to you, so you can please speak into the microphone.
Thank you. Great talk, thanks. I may have missed it. Was this system ever deployed? And if it was, how effective was it?
Yeah, so there are two interwoven pieces here. The Whirlwind machine itself was never intended to be deployed. They thought of it as a prototype from the start. Once the Air Force started funding air defense in a serious way by 1953 or 4, the Whirlwind guys plunged into designing the computer that would be used with SAGE. So ANFSQ7 was the production version of this. They actually built an intermediate one called XD1 as a prototype for ANFSQ7. And the FSQ7 machines definitely were production machines. IBM built them. We believe that IBM learned a lot about computing. They knew a lot about business computing, of course, but not that much about scientific, and certainly not about real-time computing. So they built the machines, The SAGE system certainly was deployed, starting in, I think that technically the first one was barely kind of starting to get installed around 57 or so. And SAGE stayed operational until I think about 1980. And you asked whether it worked. That's a bit of a metaphysical question. We are still here. It was never, thank God, never directly attacked. Again, we would have noticed. There were there have been ever since substantial discussion about whether it would have worked. And even at the time, I think there was a kind of in the back room discussion about, well, what is the definition of works? The public presentation of SAGE was that it was the impenetrable continental shield, and this was all going to be great. And I think in the back room in the Air Force, it was, as long as it defends enough of the SAC bases that we can respond, then it worked. Right? So I think there's a broad range there. As to whether it would have worked in the public-facing sense, I don't think anyone thought that was going to happen. That there were too many vulnerabilities, even known at the time. And of course, I mean, we're still having this argument, right? Strategic Defense Initiative, would that work? I don't know. So it's, but it was successful. Certainly in a political sense, it was successful, and militarily, who knows? It's kind of hard to tell. Yes, microphone, Jeffrey.
Well, you mentioned Ken Olsen and Len Shustak, and I wonder whether the tapes that you got decoded came through the Boston Computer Museum, whether there was any involvement by the Boston Computer Museum on the way to your project.
Yes. So let me see. So MIT decommissioned the thing in 1959. Right? There was a guy who worked as a programmer on the Whirlwind program called William Wolfe, who left Whirlwind towards the end of the program and went to form his own engineering company. He actually wrote a short memoir in which he admitted that what played out next maybe hadn't been the best idea, but at some point he decided he was going to try and buy the decommissioned Whirlwind and move it and get it working again so that he could do contract programming for the, government agencies. And he actually did succeed in getting the thing moved. I think he decided that maybe the business side of that plan hadn't quite worked right. By about 1970, his company was faltering. I don't think that was the only reason, but his company was faltering. And he announced he had to liquidate the company and announced it was going into the dump. Right? He was going to send Whirlwind to the dump. By that time, Ken Olsen had trucks and warehouses, we haven't found, the two apparently didn't get along very well, but they got along well enough that Ken learned about this and said, oh, don't worry, I'll take it to the dump for you. Yes, I'll handle that for you. Don't worry. And so a lot of the stuff ended up in a deck warehouse. Some of it, of course, ended up in the Boston Computer Museum and came here, but a lot of it came through the back, from the back room. Stuff that had been saved by Ken, went to the warehouse, and ultimately came here. We think that's where I don't know, I should be careful. I think all of the tapes came from Whirlwind, not through William Wolfe. But I'm not sure about that. Right? We don't know how to trace what happened during that decade. I haven't seen anything in the tapes that says, that looks to me like it's exclusively Bill Wolfe activities. So somehow the tapes came through a channel that Olson certainly would have known about, but didn't involve the Wolfe engineering. But most of it, essentially, it came through the channel that formed the Computer History Museum. Yes.
In this 256-word program that you're describing, was that before or after they switched to ferrite core memory?
This was before core memory.
What was the technology for memory on that?
Good question. Yes, it was electrostatic tubes.
Williams tubes.
I'm sorry?
What's called the Williams tube?
Oh, yeah, there's an interesting thing there, too. I don't understand very well. The Whirlwind guys knew about the Williams tube and somehow decided that was really not good enough for our needs, and developed their own electrostatic tube. Of course, the underlying phenomenon is the same, that it's an electron beam that leaves a spot on the face of a CRT. But they spent a lot of time and money trying to improve that technology using a little bit different approach. So the net result was it was electrostatic, but it wasn't a Williams tube. IBM, I think, 701 literally used Williams tubes, and they didn't, so neither team could get them to work very reliably. The Whirlwind guys knew pretty early on that this electrostatic tube idea was not working out so well, and the project leader, Jay Forrester, apparently himself locked himself in the back room with a couple of his guys and worked on this core storage idea until it became obvious that that was actually going to work. And at that point, they step-by-step disconnected. They did get to a point where they had 2,000 words of electrostatic memory that more or less worked. But they step-by-step replaced that with core memory and made the machine much more reliable. So it was, that transition took place about 1953. This was 2 years before that.
Great. We have time for one more question.
Thank you. Aircraft simulator. Did this thing ever operate as an aircraft simulator? Was that...
No.
Okay.
It's weird. I went back over they produced a lot of reports, right? And I went back over there was a series of reports which were kind of minutes and decisions from the executive, but from the leadership team. And it doesn't say anything about it, right? There are reports where they say, well, we're working on the cockpit design, or working on the actuators, and then suddenly we're just not. So I don't know yet quite what really transpired. Obviously, part of it was they came to the realization that, oh, this problem is actually harder than we thought. I mean, who would have imagined such a thing? But I don't know why it was harder enough that they just bailed out entirely. Whether it was the Navy that said, okay, knock it off, give up, or whether it came from the Whirlwind team itself.
Yeah. I wish I had customers like the Navy and the Air Force.
Sorry?
I wish I had customers like the Navy and the Air Force. Let me do whatever I want, whatever price tag I want.
Yeah, I know I'm saying it that way. I doubt it was that straightforward, because they really did come very close to, I mean, they had an existential crisis with the Navy. They really came very close to not having a project at all. And it was only what you might think of as a good bad luck that the political situation suddenly motivated the Air Force. Because prior to that, the Air Force wasn't particularly interested in this problem at all. Right? They had, the Army has anti-aircraft guns. What do you need? What else do you need? So they weren't up to this. They weren't onto this. It was only after the political scene changed that they decided that maybe they needed to think about this. And even then, I think a lot of it was political pressure more than certainly the entire Air Force didn't say, oh, I see, yes, we should do this. There was substantial resistance. It's interesting, in Valley's memoir, he says, convincing the Secretary of Defense that this was a good program, that was a good start. And then they had to convince everyone who reported to the Secretary of Defense that this was a good idea. And that was not straightforward either. Anyways.
All right, thank you, guys. Thank you, Guy, and everyone give him a big hand.